Okay, it's like example number 6 on the left side. If you click on it, you will see what I see. And Eric already teased in the introduction that we have the ability to connect several neuron circuits to form neuron morphologies. And we can make use of the whole capabilities of each neuron circuit. So we can not only support passive properties of the neurons like PSP propagation, but also active properties like dendritic spikes. So what you see here in this picture is 2 neuron circuits, or 4 neuron circuits, like 2 in the top row and 2 in the bottom row, but you don't see the full part of the bottom row. And we illustrated here the connections you can establish between the different circuits. So Eric already mentioned the horizontal connections, where you just connect 2 neuron circuits with a low resistance. And also we have a so-called shared line to which we can connect via a tunable resistor, or again via a direct switch. And using these switches, we can form various neuron morphologies. In this example here, we will focus on a simple chain of compartments, which you can see here in the bottom in orange. At the top, there is like the simple representation. We have 4 compartments which are connected with resistors in between. And in the bottom, you see how this would work on the hardware. So we have 2 neuron circuits for each compartment, which are connected via the direct horizontal switch. And then we use the shared line to connect the different compartments and form the chain. And the beginning is the same as in the other notebooks. We will start by setting some environment variables for the microscheduler, import pi and n. And then after our inputs are done, we load a default calibration from the nightly deployment. We set up Pine, define what kind of chain we want to have. So we have here, I take a chain of length 4, and I also define here a number of inputs. So what we want to look at is how postsynaptic potential travels along the chain when we inject a synaptic input in one compartment after another. So the number of inputs is how many synchronous spikes we send into our compartment. Now we can start creating our chain. We will use also the HX neuron we use in a single neuron demo and before in the super spike example. As I told you before, we need 2 neuron circuits per compartment. So in total, we need 2 times the length of neurons. And so I just define it. Here in the bottom, we take a view of the created population and connect each second neuron circuit to the, we start at the first neuron circuit and connect it to the right, and we do it for every second. So we establish the horizontal connections. In the next step, we connect the different compartments. So what we do is we connect one compartment to the shared line, directly to the shared line. This is this statement, and the other compartment we connect via the tunable resistor, and we can define a conductance here. We also disable the threshold, so the neurons don't spike or the compartments don't spike, so we see how the PSP travels along the chain. Here we define the external input in our next cell. So as I told you, we want to have a look how the PSP travel along the chain. So we will inject an input in one compartment after another. Here we have done a function which iterates over the different compartments and sets the neuron conductance, and also iterates over the projections and sets the weights, which we can later play around with. And in the bottom part, we iterate over the different compartments, perform a hardware run, and record the membrane trace. These membrane traces will then be plotted. And now I will start the experiment. And here we see our result. So in the different columns, we have a different recording site, and in the rows, we have different sites of injection. So in the first row, we inject our input in the first compartment, and then in each different column, we see how it behaves in the different compartments. So what we see is that the PSP, as we expect, decreases as it travels along the chain, and it also broadens a bit. And if we inject now the input in the second compartment, in the second row, we see that it travels to both sides of the chain, and it also decays to the different as it travels along the chain. And we also see that here we have an effect of the fixed chain length. So the PSP is higher to the left side because there the chain ends, and to the right, more current can flow to the last compartment, and we have a stronger attenuation. Now, if you want to, you can play around with the weights. So we can increase the input strength, and what you will see here in the bottom on the y-axis, the scale will increase. So we now have higher PSPs, and what we can also see that the noise is, or the relative noise is now, of course, a bit weaker. On the other hand side, if we decrease the weight, we will see that the PSPs get smaller, again, with the scale, and we also see the noise on the membrane. So I will increase the rate again. And we can also play around with the conductance between the different compartments. So if I decrease it, we will also see that the PSP height increases and the attenuation gets stronger. So we always have no response here in the last compartment, for example. If we increase the conductance, the PSP heights get smaller again, and the attenuation is less strong for the PSP as they travel along the chain. So that's it from this notebooks. Feel free to play around a bit. And if you have any questions, let me know or let us know. I think maybe you get now some time to play around, get to know the notebooks, and at any time, if you have a question, just speak up or let us know in the chat.